All right, so I'm going to start here with electron configuration, section 2. And so we're going to start actually with the electromagnetic spectrum. So I'm going to slide down here in the notes and just jump ahead a little bit, and we'll come back to it. So there's the electromagnetic spectrum. And you can see that rainbow in the middle, that's the only thing that we can see. We can see the visible spectrum, which is a very small part of the electromagnetic spectrum. We got all kinds of things in there: X-rays, radio waves, infrared, which is your TV remote, ultraviolet, which is the sun. There's all kinds of things in there that we cannot see that are still part of the energy that is basically part of this electromagnetic spectrum. So what we want to look at specifically is the wavelength and the frequency, and start to sort of understand some of those concepts. So we'll slide back up here, and it's all going to come down to the concept of a wave. And a wave function, when we look at the electromagnetic spectrum, we're going to be looking at wavelength, which is the distance between the waves. And then we're going to look at how that relates to what's called frequency. Now, frequency is how many of the waves go by in a certain amount of time. So if we're just talking about a person, so like you, and then energy is hitting you, so that could be UV or IR or visible light or whatever the energy is that you're being affected by. If it has a longer wavelength, then you're going to be affected by less waves over a certain amount of time. So if we have a big, slow, long wave, that's not going to be a lot of these wavelengths going by in a certain amount of time. So what we call the amount of waves that are moving by in a certain amount of time, we call that frequency. Okay, so if the frequency is low, it means there's not a lot of waves going by in a certain amount of time. So this would be considered low frequency, because see, the wave is really long, but not many of them are going to go by, let's say, in a second. Well, we could go ahead and do a different wave. And now we could do a wave that looks like this, and we could kind of pretend that it's the same amount of time as our last wave. Well, that frequency is going to be higher because the wavelengths are now much shorter. So a lot of them are going to go by in a certain amount of time. So this one we would say is a high frequency, and it's going to be a low or short wavelength. So what you can see is wavelength and frequency are opposites. They are inversely related. Now, I would like you to write this down in your notes. So just write down somewhere in your notes that, I'm just going to put it down here, but you should probably put it somewhere else. I'm just going to put it in this box. You want to write down that frequency is going to be for us the same as energy. So if we have a high frequency, we have high energy. If we have a low frequency, we have low energy. So we just want to understand that these are basically the same concept. All right. Okay, so let's kind of look at what we have up here. They gave us the variables for wavelength and frequency, and then here's a mathematical formula, which is the speed of light and its relationship to the two. They gave us the speed of light right here. This is in the IB data booklet. Here's the conversion to go from nanometers to meters. Why would you need that? Well, a lot of times we measure things in nanometers because they're very small. I mean, the waves are very small. But the speed of light is in meters per second, and so then nanometers and meters are not going to play nice. So we'll have to convert. Also here's the unit for frequency, which is hertz. Now, hertz is actually per second, so it's cycles per second. So it looks like this, 1 over s, or s minus 1. And then down here you can see Planck's constant, which will allow us to get energy calculations. And then we can go ahead and look at Planck's constant, which is a number. And then that number can go ahead and be plugged in to solve mathematically. So let's go ahead and clean this up and let's just do a quick problem. Now, these problems are really easy because it's just you're just plugging a value into your calculator and it's kind of spitting a number out. So not particularly difficult. And so this one says that we have the red light from the aurora borealis, and they said that it is emitted by high energy or excited. So excited means electrons are not in their normal energy levels, but we'll get to that later. And that they're at 630 nanometers. What is the frequency? So the nanometers are going to be a problem. Why is that a problem? Because here's the formula we want to use. Speed of light equals our frequency times our wavelength. Well, it says find frequency, right? So I'm going to have to rearrange this. And so the speed of light divided by my wavelength is what I'm looking for. But again, I'm going to be using a C value. So if we kind of set our problem up, V is going to equal speed of light. Remember, given to you in the data booklet. Don't have to memorize it. So speed of light, which is 3.00 times 10 to the 8th meters per second. So like that's not helpful, right? Because I can't use nanometers and meters. So I don't really want to convert this. So we're going to keep this as it is. And then we're going to go ahead and convert the other values. So we'll just set up our problem. But we've got to figure out the number that goes to the bottom. Well, the number that goes to the bottom is that 630 nanometers. I just don't want it in nanometers. So let's just convert that real quick. So 630 nanometers. If we look at our conversion, for every 1 meter, you can see the conversion right here, there's going to be 1.0 times 10 to the 9th nanometers. So the nanometers are particularly small. So it takes a whole bunch of them to make up 1 meter. So when you run this through, you've got a 10, that's not a very good looking 10 to the 9th, so maybe I should redraw that real quick. So 1.0 times 10 to the 9th. Now I'm just going to put this into scientific notation. Now you can just run it through your calculator, but I'm going to make it 6.300. So see, I moved the decimal 2 spots to the left. So normally this would be times 10 to the negative 9th, but since I moved my decimal twice, it's going to be times 10 to the negative 7th. And you can just run that through your calculator and you'll get that. But now this is meters, and so then that'll play nice right here. So let me go ahead and squeeze this in here. 6.300 times 10 to the negative 7th meters. And so what you'll notice is that your meters are going to go away, and you're going to be left with 1 over seconds. Well, 1 over seconds is the unit that we want, because that is the unit for hertz. So we'll just run it through our calculator, and we're going to get an answer. And so just take your calculator, run that through real quick, and see what you get. So I'll do it as well. 3.00 times 10 to the 8th. And then divided by 6.300 times 10 to the negative 7th. And you're going to get 4.7619, etc., times 10 to the 14th. Probably should go to 3 sig figs because of the 4 sig figs, because this is actually a conversion factor. So we'll go to 4 sig figs. And so with 4 sig figs, we're going to go with 4.762 times 10 to the 14th. So kind of a big number, but basically what that means is that this is a lot of them are going to be going by in a second, and so that's why you have the large frequency. So, all right, now we got example 8. So try that here in a second.